Perfetto. Yeah. Right. Okay. Now we will introduce a seminar, which is, if you want, related to the microbiota impact onto rocks, which was the theme of this training school. But because we are sitting in an area which is on top of a series of volcanoes in there, I think it was a good idea to introduce to the whole PhD community of this project to the, I would say, the Campi Flegrei volcanology, but I will say also geophysical problem related to the active zone in this part of the planet. So I had the chance to find and invite Grazia Delandro, which is a researcher at the University of Naples. She's a geophysicist. She graduated in Naples. She did a PhD in Bologna. She did research in various parts, including Grenoble with Virier, and then in Stanford with Tiziana Valorio. So, and now she's also working in that area. I think your background is essentially a seismologist, sensulato. So I think it's a real pleasure to introduce her and to hear what she has to say about that area, which is a quite, I would say, controversial area from a geophysical and geoscience point of view. And I think it would be great to see a good introduction to that. Thank you very much.
Thank you. So, first of all, thank you to the invitation to be here with you and discuss about this very hot topic, not only in our community, but I think in our city in this case. And since most of our colleague lives in this area, so it's something that touches us directly. And indeed, each time there is a significant event, we start to text, did you feel it? Did you feel it? And then we can directly have an impact of the earthquakes. So my idea for this presentation is to discuss with you more or less the main advances in the research in this field. You surely know that the geophysical investigation is not always easy to not to handle, but the interpretation of our data is not univoc. So we can have different information, different application, different physical parameters that can tell us contradictory information. And this is the case of the Campi Flegrei area. Very briefly, I want to thank all the people that collaborate with me for constructing this presentation. My background is not a volcanology, so I asked to Mauro De Vito and other people of University of Naples, Federico II and INGV to help me in this presentation. I'll briefly describe the volcanological history of Phlegean fields, just to understand what is the background. And then rapidly, I want to introduce the main manifestation of this, that is the bradyseism. So how we can understand what is going on. These are our observations. Then I will describe the different and controversial hypotheses of the bradyseism origins. Briefly, how we can look for the magma chamber within this volcano, since we know that a volcano needs to have a magma chamber to be active. Something about the current crisis that is very peculiar and that is still ongoing. So something that can interest us nowadays. And then very briefly, since it's not my topic, just a few slides about the risk assessment and how we can do for mitigation actions. So here I cannot point, okay. So you can see this is the Campi Flegrei area. Okay? And the Campifrene is a volcano within the Neapolitan volcanic area that includes also the Vesuvius and the Ischia. So we are in a very rich land in terms of volcanic activity. And the Campifregrei in particular, that is here, consists in two nested calderas that came from two different eruptions. I'll explain you briefly. But the very peculiar aspect is that it's located in a densely populated area. And you can see with your eyes this. You can see here, for example, I put here a figure of the Solfatara crater, that is this one, so very near where we are. And then you can see all the buildings all around the crater. And you can see also the very intense magmatic emission, the gassing in Solfatara. So this is a very high populated area. So this increase, of course, the associated risk of this volcanic area. And then we have that over the past 50 years, the inner portion of the Campifrene caldera, then I show you some more detailed figure, experienced three major uplift episodes. So we have this one, 82, 84, that is the one for which we have more data, of course. And then we have this one that is still ongoing. So started in 2005, more or less, and then it's still ongoing. As I said, there was different eruption that was affected this area. We have the Monte Nuovo, that is the most recent one, and the two main eruptions of the Campania in Imbrite and the Napolitan yellow tuff. You can see here the different shape of the calderas, nested calderas, obtained from this kind of eruption. But the portion that is interested by, this is the Monte Nuovo, you see, so the last eruption. The area that is interested by the uplift is near within the inner caldera portion. And here you can see the different craters of the major eruption in the last 13,000 years. You see here the Solfatara, so the ones that I showed you before. You can see here the Capomiseno, the Baia, we are more or less here, so we are in this area now. Then there is the Monte Nuovo, Gauro, Cigliano, Astroni, and Dagnano. And this is Nisida. So you can see only by looking at this picture how many craters we have in this area. This can give you the idea of the potential impact of this kind of volcanic hazard. Interesting thing is that the erupted volumes changed not only in entities but also in direction. So you can see that the first episodes interest the outer caldera, and then the eruptions start to collapse within the center of the caldera. And this center of the caldera is corresponding to the center of the uplift. So it's something that we can say that these different manifestations are related among each other. Then, what are the different aspects involved during the unrest crisis? So we have not only the first manifestation is the ground deformation. Here you can see the uplift range starting from the maximum uplift that is here near the Kusoi town, and then you can see how the uplift change. So it's the central part of the inner caldera that starts to have this uplift, especially in the central part, and then you can see how this vertical uplift is accompanied by seismic events. It's not something that starts rapidly. You see that the uplift starts slowly, and then once there are significant changes in the rate of the uplift, the seismicity starts. And then you can see how the cumulative of events, that is the blue curve here, follow the vertical uplift rate. So the vertical uplift change, the seismicity increase. So it's clear by this simple observation that the two mechanisms need to be related. There is another interesting thing, that is the temporal evolution of magnitude, maximum magnitude and maximum depth. This is something that starts with few events with low magnitude, and then increasing the vertical uplift means an increase of the maximum magnitude and the maximum depth. So the seismicity starts from the top and comes to the bottom by increasing also the magnitude. This is the distribution of seismicity. You can see here, these are the figure provided by the INGB bulletin. Then I explain later briefly what is the monitoring strategy of the INGB. And you can see how also the distribution of seismicity has this with ellipsoidal shape that is very coherent with the shape of the uplift. So not only in temporal evolution, but also in spatial distribution, we can say that these two mechanisms needs to be correlated in some way. Then these several earthquakes, especially the most recent one with magnitude higher than 4, raised concern among the population. Since it was quite shallow, and then the ground shaping was strong, and this prompting calls for an updated and reliable risk assessment. There are different manifestations of the gravity size. This is one of the different ones. You can see here the Serapeum of Pozzuoli. So it's a monumental area. And you can see in the different years, different level of water within this area. How is dry here and how was in the 1950. Then we can use the 3 tallest marble columns to measure the level of the water. And this Bradley size calls the uplift of this area by the fluids that flowing away. And then this is one of the manifestations. There was also another manifestation about the ancient port of Roman area that came out of the water. So there are different observables that can tell us not only the measure, of course, of GPS, but also this large-scale manifestation. You can see here from 90 to 2012 how the uplift change in time, and you can see here that there was a first small gravity size crisis and another one in 1970 that was quite well measured in terms of uplift, but not in terms of seismicity, since there was not any recording network. Then there was another gravity seismic crisis in 82-84 that was well recorded also in terms of seismicity, since different researchers from University of Wisconsin came here by installing a local network. And then we have also data, seismic data associated to this crisis. Why it is so important? In order to understand what is the mechanism of the arrest, we need not only to well record the different observables, but we need also to compare what is happening in the different episodes. And to do so, we need to have data, of course. Then you can see the intensity of the uplift. The value of the uplift is 120 centimeters in 12 years. That is a lot. It's a very huge amount of uplift. If you compare this value with other calderas like Yellowstone and other kind of volcano in the world. So it's very, and as I said, the very peculiarity is that the Campus Legrei can accommodate a lot of uplift before to start the seismicity. So area that allows to accommodate this intensity of stress and uplift before to crack and to generate the seismicity. This is something that is very important for our discussion. Then here, as I said, it is very important to compare the different crises. Since you know, each unrest crisis can evolve in an eruption. So it is very important to follow all the evolution of the unrest crisis to understand what's going on and to have an idea on what can happen. This is you can see here a comparison between the seismic events of 82-84 crisis with the seismic events of the current crisis. And you can see how the increase also in this case, the increase of uplift cause an increase of the seismicity is quite the same of this current crisis that is still ongoing. So this kind of comparison is very important. You can see how at the very beginning, of course, at this scale is not easy to see, but at the very beginning, where the uplift had to come, the seismicity is quite low. And then once you can see this rapid variation of uplift, you can see the bunch with the seismicity rate. So also in this case, we can see the effect of the bell-shaped deformation. So the deformation, we have several GPS stations in the area. The INGB, not we. The INGB had several GPS stations in the area, and from 2000 more or less, they added also OBS station to measure the GPS speed of offshore. So we have several stations inland and offshore to measure and to interpret the uplift, and then we can see the bell-shaped deformation of this. And then we can measure also directly, as I said, from these different areas. So the Serapeo, the Portus Lulus here, and the uplift also of the submergent Baia, how the deformation change not only in time but also in space. That is an important information to compare this with seismicity rate. Different are the models that was developed to explain the bradyseismic phenomenon. So there was a very extensive scientific literature over the past 40 years about this. And as you know, the same data can give different interpretation. So about the seismicity, we have not only the 82-84 crisis, but we had also several marine active experiments that gave us information about at least the deep magmatic source. And this different interpretative model can be divided into 3 different categories: the direct involvement of magma in the uplift caused by the deformative processes related to the expansion of the surface hydrothermal system, and then the combination of these 2 problems. And the real scientific question is, can be the magma at shallower depth? The first hypothesis is that you have here a quite well constrained deep magmatic source at about 7-8 kilometers of depth. Then you have the direct migration of magma that claims for difference in pressure in the shallower area, and then directly the magma at the peak of magma can act as a source of the uplift, so the deformation. This is the first interpretation. Then, so you should have for this kind of interpretation a magmatic source between 3-4 kilometers depth. Then the second hypothesis is someone related to the degassing of magma. So you have this magma that rises up to 4 kilometers depth, more or less. There is here different lithology from the deep magmatic source. Then the degassing of the magma causes the uplift, and you have this uplift at the center of the biosensor. And then there is a third, and this hypothesis is more related to the gassing. So it's something, plume of gas that rise and can cause the expansion. Then there is, and so this is a sort of mixed hypothesis, magma and the gassing. And then there is also a third hypothesis of the origin of the bright ice that claims for the supply from the deep magmatic source of this more shallower reservoir, but gas reservoir, not magma reservoir. And this is a spoiler, we are more for this kind of interpretation. Then I show you why from our side. So there is a common point among these three hypotheses, and that comes from also the observation in other kind of calderas. You should have a magmatic source to feed the system, the superficial system. Then the first two hypotheses require the presence of shallow magma. And to support the third hypothesis, there are very contradictory evidence of magma presence at shallow depth. There was several papers in this last year that claims for magma presence at shallow depth. You know very well that you need to have the resolution in terms of geophysical inversion to say and claim to see something. And we are very, not limited, but very related to the distribution of seismicity if we want to use passive data to see something. So if we have, as I show you, the seismicity up to 3.5 kilometers, more or less 4, we cannot say that we can see something below the seismicity. So this is strongly data related in our opinion. Then there are evidence of gas reservoir at depths between 2 and 3 kilometers. I'll show you why. There are evidence, and this is something that is very important, that there is a layer, of rock that confines the gas reservoir, the so-called cap rock. And we can see that from laboratory experiment, this cap rock has a fibrous material, and that can facilitate the transfer of the deformation from the deep gas reservoir to the surface. There was a lot of active experiments, active surveys to investigate the deep magmatic source of the Campi Flegrei areas. There was Tomoves in '94, where there was different source and arrays inland and offshore. Then there was Tomoves in '96, Mareves in '97, and Serapis in 2001. And you can see that there was several distribution of source and station inland and offshore. So a very well covered experiments. With Serapis, there was also OBS, so station offshore and the inland station. And these very extensive experiments allow to study at least the first barrier rim of caldera. This is a work of Judener Kenzolo of 2008. And here you can see that the P-wave tomography was applied on transmission wave within the experiment. You can see here, maybe it's not so, you can see here is the coastline. So the explored region was more the outer caldera world. So they have the resolution to see very well. You can see the increase of velocity, P-wave velocity related to the inner caldera world. That was very well correlated also with the gravity anomaly within the caldera. So these experiments allow to well precise delineate the outer rim of the caldera. Then another important results came from the reflection tomography by using the data from Serapis. In the work of Zoll et al. 2008, the authors defined interfaces came from velocities that they converted in rock properties. So you have at more or less 7.5 kilometers depth, the magma source, the magmatic source. Then you have this part up to between 4 and 7.5 of carbonate bedrock area. And then you have this metamorphic rock between 2007. And so they found another reflector at 2.7 depth and another shallower depth with the reflector with a very high variation of velocity at more or less 0.7, 0.6 kilometers depth. So they identify different layers in the structure of the solfatara, of the Campi Flegrei caldera, and especially they constrained the deep magmatic source. That was something that was not seen before. So starting from this, what are the still open questions, I say? There are some other shallower reservoir of magma, in our case in the Flegrei fields, that can be the source of the next eruption, since you can understand that having a magmatic seal at 7 kilometers is not the same to have magmatic seals at 2 kilometers depth. So claiming that there is magma at 2-3 kilometers depth prompts call for an update version of the hazard and mitigations and so on. So it's something very strong to say. And our as a researcher need to be pretty sure before to say something. So far, in our opinion, geophysical methods that involve tomography, seismic reflection, I don't know, something that is related to the uplift, so numerical simulation of source of uplift and so on, have not been able to detect shallower magma seal. Is there an opaque connection between the several magma layers? So some recent papers claims for different lengths of magma at different depths, but still we have not the resolution to see these different lengths with the data that we have now.
How do they make that clear if you don't see them?
Yeah, they mixed the data from 80 to 84, the data for the first years of the recent unrest, and they've done 4D tomography, passive 4D tomography. So you can teach us that the 4D tomography, the passive 4D tomography is something that is very complex to handle, since you have not the same geometry of source and station in time. Then you need to have a lot of data to have the possibility to divide your windows in temporal view. And then you claim to have the resolution below 5 kilometers with all the seismicity up to 4.5. If you have 10 events below 4 kilometers, you do not have the resolution to see below 4 kilometers. So I say that they claim, but okay, this is not
Not the request, so I have to carry on requesting.
Yeah.
Have you got the next slide back?
Yeah. Back?
Yeah, the previous slide.
Yeah.
The previous one again. The previous one.
This one.
No, the previous one again. Okay. I don't remember exactly the literature now.
Yeah.
The experiment Serapis was an array of active seismology. So you had the air gun, which was the main source, or it was the chillers.
No, air gun.
Okay.
With the
Serapis
ship.
Yeah. What was the array with the?
This is the part of the ship.
Okay.
And the triangle was the stations.
Right. What was the offset between the station Sorry,
These
the offset
distance.
between the geophone which was acquiring, the offset was 25 meters, 100 meters.
No, was I
Right.
think 1.5 kilometers.
Right, so you are telling me that essentially the grid of the geophysical instrument was quite large.
Yeah.
Which is probably the big limit of the
Yeah,
resolution.
the resolution.
Of the
Yeah.
of the times.
Yeah.
There is an intrinsic limit.
Exactly.
Of the grid. Okay.
Yeah.
And the nowadays is that the same, I mean, it's an array of sources in 3D on the seaside.
Yeah.
It was an active experiment again.
Yes, it was an active experiment.
Okay.
But the distribution of the seismic source was quite the same. So we cannot claim a resolution lower than few kilometers in this case.
Okay.
And especially the shallow part,
Okay.
that was the most not well constrained in this case.
By using a concept that we got on hands-free exploration, what is the beginning of the actual beginning of the array, which is measuring the P wave arrival using passive seismology?
In this for the passive
What
seismology,
is the
the
I will call it point in arrival, which is the distance between the geophone.
yeah,
Which are
the maximum distance is quite I think lower than in this case,
Right.
but not lower than the order of kilometers.
Right.
So we cannot go
So
deeper.
from a mathematical point of view, I mean, I guess, which is if you use the resolution of the sampling using by the
Yeah.
receiver of a source, the passive or active, I guess.
You
there's
should
a
not
limit
have
of-
a very small resolution. But the difference in this case is that we have in the last 2-3 years more than 800 events. So if you look at the events and not on the station, you can see that we have in the volume that we want to image a lot of events. That was
Right.
in the investigated area. I will show you this kind of information.
What is the knowledge of the velocity model in the array?
Yeah.
You will show, okay.
I will show. It is very important. This is a very important question, since it's something that we claim in our work that we hope will be at least accepted, is that we started from the wells in the area to construct velocity model. We don't use velocity model that comes from data. We start from wells to constrain at least the very shallow properties that are the most complex one to handle by a 1D inversion from data and so on.
By
So this
shallow,
is
you mean the deepest well, I mean the deepest.
2-3 kilometers,
Okay.
San Vito. I'll show you.
Very good.
Yeah. So this is the main problem of this kind of application. The deeper part was very well constrained, but they have no resolution to say something more than this. That is essentially a 1D model. So you can see some interfaces. You can try to interpret this with the IVO, so the impedance contrast to say this. And then there are still open questions. So how about the superficial part that is the most interesting one in our case? There is some open connection between the different magma layers. And can we say something by using the new data? As I said, we have in 82-84 crisis, the, let's say, resolution to records more or less, I think 12,000, more or less. You know that also all the instrumental part is very different. So we improved our capacity of detection of events, smaller events. We improved the density of stations. So of course we are comparing different cases. But then our claim is that we can, with the current crisis, the events from the current crisis, and the knowledge from the wells and from rock physics experiments, say something more about this very shallow part. And this is very crucial to understand the arrest mechanism. Just few words about how many time I have?
You have 10 minutes.
Okay, I need to worry. So here, okay. Okay. Here I show you briefly what are the monitoring system of the monitoring room of Campi Flegrei and all volcanic system of Naples. You can see here all the monitors that are used to check. There are also automatic procedures to detect events in continuous and semi-automatic procedure to locate events. And the data are directly sent to the Department of Civil Protection from INGB. You can see here that there are, sorry, it's in Italian, there are different measurement instrumentation. There is the seismological network to record the seismic events. There are the GPS to record the deformation of the ground. There are the mareographs, so OBS but offshore. There is also a temperature monitoring network, so we can also use this other information to constrain our measurements. And there are also several geochemical stations that are very crucial, since I don't know how to say in English, the elephant in the room. Come si dice in English? I don't know. Okay, the elephant in the room. Okay, the elephant in the room is that we have in the Solfatara area here. There is something that here, the same crater that I showed. We have the most huge degassing area in the world. And all these manifestations are accompanied by a huge amount of CO2 degassing. So this is something that can be also taken into account in this discussion. I still don't know how, but of course, this is another geophysical and geochemical very important information that we have continuously by the monitoring system. We have the isotope, CO2 on CO on different things, the flux of CO2, the temperature. So of course, also this kind of geophysical information needs to be taken into account if we want to say something about the unrest mechanism. I don't know how. And then there are also monthly surveys to measure the isotopic composition of the degassing system. So you see that we have a lot of information coming from multi-physics and multi-parameters observation. And then you can, there are several communication that the Osservatorio Vesuviano needs to provide related to these three observations that are used to define the alert state. So the seismicity, the deformation, and the geochemical composition of fluids are the ingredients to define the alert that is yellow at the moment and is still yellow from the beginning of the crisis. Then let's come to the current crisis by looking into details the distribution of seismicity. I already showed you this graph. That means that there is a vertical uplift that is followed by an increasing of seismicity. And this graph means that with the increasing of uplift, the maximum depth of seismicity increased and the maximum magnitude of seismicity increased. So these are the data. Then I show you here the distribution of events. You can see here in time, this is temporal scale by color, and then you can see how here is more clear. The ellipsoidal shape of the seismicity is very well coherent with the ellipsoidal shape of the deformation. You can see that the seismicity starts more or less here with this very light blue, then start to be wider, and the depth seismicity is located here. Then I show you more in details this. Just
sorry.
Yeah.
Do you have like visual models of this seismic events in this map? Like just to have an idea about this fault or like the shallow fault orientation.
Yeah, I'll show you. This is very important, the seismicity distribution. Since the first part of our analysis starts from the seismicity. So we used a new location code developed by Lomax. I don't know if you are familiar with, that use optimized velocity model and updated station correction to improve the seismicity distribution. I don't know if I can show you. Okay, so we applied this new location code by using all the stations that you can see here. These are the stations. These triangles are in 3D. And then this is the distribution of seismicity. And scale is the magnitude, the color scale. And also the dimension of the events is related to the magnitude. And then we obtained this very high quality distribution of seismicity. You can see how the seismicity is distributed. You have this very depth seismicity offshore. The most of seismicity is here below the Solfataro, and then you have this seismicity here that is related to this new fault. I'll show you the sections, and all the seismicity has this ellipsoidal shape. I can show you also the distribution in this other direction, and you can see these alignments here, these alignments here, and another important thing is that the higher magnitude events are the deepest one. You can see this. The higher dimension is in the deeper part, and this is very important in our idea of what's going on.
What is the uncertainty on the location of
It's very low, lower than, I think, lower than hundreds of meters. Since this new location codes allows you to account for the inconsistency of the velocity model by updating the station correction in 3D. So you construct not station correction for station, but you construct station correction using the distribution of 3D distribution of events. So you can account for common anomalies in residuals. That means common anomalies in velocity. So it's very, very developed in 2 years. Yeah.
I know that yours is actually, but
No.
what are those points on the left, on the lower left?
This one.
Yeah, those are located in the Bahia, right?
These are located?
In the Bahia.
Yeah, offshore. Are the deeper one that are offshore in this area.
And what's the explanation?
See, are farthest from the distribution in this case. Yeah, of course, this can be related to some location errors for events that are farthest and not well resolved. You can see that, I can show you the distribution. The accuracy of location strongly depends on the station demand. So of course, if you have events that are here, you have this station here, but here the density of station in this area is lower than the density of station in this area. So you can expect that the resolution of events here is lower than the resolution of events here, since the distribution of station, of course, affects your resolution. Especially if the events are smaller, that means that you have less station to constrain them.
What's the difference with the resolution offshore and onshore then?
You have,
I mean, the ranges.
you have this station here, this
Yeah.
station here, and this station, this fourth station that you can use to constrain. Then we have the also offshore station. So for all the events that are at least within the station, we can see that are well located. Then, of course, you can have some events, you see, especially this one, that can be on the border of your grids. That means that are not well located, since you define the grid, and then the events is at the border of your grid, you can say that
So
it's
that
well
means it
located.
can be anywhere in between the stations.
No, it cannot be anywhere. For each event, you can define a probability distribution of the occurrence of events. And from this probability distribution, you extract the event's location and the errors associated. So we can control, of course, what is the error of these events. In this case, usually, when you look at the distribution of seismicity, we do a selection of location probability. Otherwise, you can see a lot of very small events that are not well located. So of course, you need to look at also the resolution of events if you want to see something. Yes.
Yeah, but I was just also this question could be distributed. But the seismicity is correlated also with the uplift of the area, right? And so you could kind of predict where a future eruption will be, or this is not possible?
No, this is the idea to
Okay.
use the passive seismicity to image the velocity. The basic idea is that you can see the magma as a contrast in physical properties of the medium. So if you can reconstruct the velocity within the medium, you can say, okay, here I see a very high velocity patch. I can see that this is magma. So you use the information that came from the events, that the elastic wave generated by the events travel to hold your medium. And then you can take this information and then backtrace this information to see what is the velocity within the medium. And then I can see if there are some very anomalous value of velocity. You can say, okay, this is magma. Of course, you have a determination. For this, you need to use complementary information to say.
And what if the reaction is not related to magma emissions, but just gases? Can you predict?
This is a multi-risk area. You have the seismic risk, you have the volcanic risk, two different risks. Of course, also an events 4.4 as the one that we had in the last crisis can be risky if you have buildings that are not constructed as they have and so on. So it's something multi-risk. Of course, if you have an eruption, you will involve a volume that is wider than seismic risk. I'll show you some picture after. And then here very rapidly a distribution of seismicity with the main fault. So a question that was posed before. You can see how the seismicity aligns. If you look at smaller section, you can see how the seismicity aligns with these pre-existing faults, especially in the at the inner caldera borders. So once you see this, you see that, for example, in this area, you have very pretty well alignments with the faults that was in the caldera border during the formation of the caldera. So the distribution of events is very coherent with geology, with structures that we expect in the area. And here is just to emphasize that events with higher magnitude are deeper. Yeah.
Sorry for the question.
No, no.
Those two points in there are related to some faults.
Yeah, yeah. The alignments that you see means that the events belong to some similar pattern of fault. So fault plane. You can define a fault plane by looking at seismicity. Of course, this is very complex to say, okay, why, for example, this cluster is not aligned. All the seismicity, the trigger and seismicity mechanism that trigger seismicity is not uniform. You can have, for example, the depleting of the reservoir that unlock your flow. You can have direct gas that travel through your medium and you can trigger seismicity. So the different mechanisms cause a different distribution of seismicity and behavior in terms of parameters, source parameters, I don't know, the stress drop, all the parameters that are related to seismicity. Is something very technical. But yeah, the alignments tell you that you have a fault there.
Plastic levels A, as I was seeing before.
Yeah, yeah. This is the same distribution of seismicity color-coded by the depth. So you see different color by different depth. Yeah. No.
The previous question, previous slide. So okay, I understand you kind of map it and kind of relate it to geological causes, yes. But have you then trying to pinpoint like different sets of events in different times, whether they correspond to the same fault, same degassing event?
Yeah, yeah. The temporal evolution is very crucial in this case. I'll show you after a slide. Then, what is the key question in this case? We have all these informations. We need to relate we need to relate all this information. So we want to use this information that comes from earthquakes, passive earthquakes, to image our mediums in terms of velocity properties of the medium. And then we can use the anomalies, as I said, to say, okay, this anomalous velocity can be associated to some physical properties of the material. And then after, how the seismicity behave respect to this structure that I can identify, since the two things need to be correlated. And then we used the current seismicity and the very high quality location that I show to obtain iteratively, I will not go into details, the velocity, the tomographic velocity image that I'll show you here, by reaching a resolution of the order of 200 meters. So very high resolution volumes. I show you here only two sections, just to be clear. You can see these first two are the section AA prime that cross the inner the inner crater, and then the B prime is the section that is south-north. And these are the two sections that we obtained in terms of velocity, BP, and in terms of velocity, BP over VS ratio. We have two kinds of waves, you know, the P waves that are the primary waves, the S wave that are the secondary waves, and the two different waves sampling the medium differently, since are differently polarized. And then we can, at this point, use not only the information that comes from the BP, but also the ones that comes from the ratio, that is very sensitive to the fluid content of the medium. Then you can see how we can the BP tells us that there are different, you see, different shape. You see this shape of the funnest shape of the basement here, so there are some important information. But then the very impressive figure that we obtained is the one that comes from the BP over PS, very high resolution. Why? You can see that the blue is associated with high BPBS, and the red is associated with low BP over PS. And the high BP over PS, and of course, this behavior can be due both to the rock matrix and to the fluids that is within the rock matrix. And so you can see here very clear this, how to say, this arch-shaped anomaly, high BPDS anomaly. You can see also this here, that is associated to the caprock, so the ones that I discussed before. And this very well-defined volume, ellipsoidal volume, that can be associated to the gas reservoir within 2 and 4 kilometers there. So we can say, I don't want to go too much in the detail. These are the information from the wells. These are two wells, San Vito 1 and San Vito 3, that are more or less at the border of the caldera. And you can see that this kind of lithology are very coherent with ones that we found in the wells. So we compared the velocity model that we obtained with the typical velocity model for the formation from the wells by considering different fluids within the rock matrix, and we found that this high BPBS is related, can be associated to the caprock, and this low BPBS can be associated to the gas reservoir in the first shallow depth. So this is a 3D image. The section is the one that is shown here. You can see the 3D picture of the gas reservoir and the well-shaped, arch-shaped caprock is in blue. And then you can see also that the very first events start in the caprock, and that comes to go down by increasing depth and by increasing magnitude. Why the caprock is so important in this case? The caprock is so important since can accommodate a lot of strain. This is the reason why we have a very huge amount of strain before the seismicity increase. Since there was a work of Van Orry et al. On Science in 2015 that characterized a very smaller scale. You can see here the micron. This is micron, 5 micron. So at laboratory scale, very small scale, the microstructural characteristics of the caprock. They had samples extracting from the amplifier, so at the depth corresponding to the caprock, and they found within the caprock the fibers. So it was very unexpected results. And these fibers that was naturally growed due to the hydrothermal conditions, allow the caprock to have a higher strength and to before to crack. There was some wells, yeah, there were some wells in the 80s, more or less, from the Agip.
And let's just say this.
Huh?
Let's say, let's say that all the CO2 or all the gas in there and get through the oil. What happens?
The escape path is not the well. I not go into detail, but you can see here near the solfatara where you have the gassy that this blue is interrupted by a green. So you have here a variation of the PDS that can be associated to the fracturation of the medium and to the flowing of this gas throughout the surface where the gas in occurs.
How do you know it's gas? It's not time.
We can also, yeah, the BPDS value that we found, we have also laboratory experiments. So we had samples from the reservoir, we used a different fluid saturation within, and we measured the BPDS under hydrothermal conditions. Since the thermic and pressure conditions here are very peculiar. So if you want to simulate, you need to use exactly the same. I don't have here all the measurements, but we used rock physics laboratory experiments to constrain these
So
values.
it's a for certain there is this reservoir and just gas and no matter.
No, exactly. Also in terms of velocity, in terms of shape, we can say that this is not magma. And we have also the basement there, but the very interesting thing is that we detailed the shape of the caprock. So this is something that was not already seen before. So this caprock, characterized by high BPDS, is, you see, it's deformed. So this can accommodate a lot of stress before to generate fracture.
May I ask you a question? I mean, from the old data set, the old.
You cannot do for the tomography.
No. I would just have something more simple. Do you have some scientific line, more scientific line, I mean, raw data, where you can match the ABO analysis from the raw data with test data?
We are doing this.
Because that would be, I think, really the smoking gun. If you have the same ABO response, coinciding with that one, no discussion.
Yeah.
Because the ABO is robust.
Yeah.
If you have in a situation with data on the road.
Yeah, we are trying to arrange our data to obtain the migration is not simple.
Yeah, it's not simple, but it's 2 kilometers, 1.5 kilometers. How much is that discuss rental? This is the top of the.
This is a couple of kilometers in this direction and 3-4 in this other direction. So it's not so smooth, but.
You just need a couple of seismic lines which go a little bit deeper and.
Yeah, we are trying to look at this, and this is something very new. Indeed, we had a lot of problems. We have a lot of problems to explain this. To explain this to the scientific community, you know, an idea that is different from the current ideas is different to.
Are those scientific profiles this published this reservoir or like if I remember correctly, all those were very scientific.
Yeah, but was in 90, so it's something that we cannot use now. No, we are trying to do radio analysis with passive data, the current one. So the very difficult thing is to find the right geometry, to arrange the data, you know, it's not simple because we have different magnitude of events. It's not simple. So we are trying to.
How do we measure pressure for magma part? You said beside the BP to BS ratio, we don't need to have the pressure values as well.
Yeah.
I'm just wondering how do you measure pressure for magma?
But you can use a more or less constant gradient. So you have by changing the depth, and we have also the pressure from the wells. So you can check if this can be associated. And anyway, when we apply this pressure in laboratory scale analysis, Do you have pressure points for magma bars in wells? But wells cannot reach the magma that is deeper. Yeah, but the pressure gradient is different. Yeah, different formation and different floods. So of course, you can have a different gradient by considering different lithology. We use an extrapolation of pressure with depth, and we check it that at least at the maximum depth of the wells is consistent. 4 minuti, ho finito. So, and then you have this gas-dominated reservoir, and the very interesting is that you can see how this shape of the gas-dominated reservoir correlates very well with the shape of the deformation. So we are discussing about the same quantities. So there is a relation between this. And another interesting is that the seismicity starts within the cap rock. Then you have here these events. They are not very visible, but are more or less all in here. You can see a very well alignments here. And then you have the seismicity that start to come up under the solfatara during the depletion. And then once the reservoir depletes, you have the unlock of these boundary faults that start to have the rupture. And the rupture is higher here, since you have already existing fault that can accommodate a lot of stress. So also the temporal evolution of seismicity is pretty well coherent with this. You can see, it's not very visible, I'm sorry, but you can see in time that the seismicity starts in the central part, then some benches here, then the solfatara, and then you have the seismicity of the border during the detection of the reservoir. So our results are very coherent also with the distribution in time of seismicity and distribution in space of seismicity.
Just a quick one. Does any of those faults that are important for this area come deep enough to have contact with the magma chamber? Because in that case, the
can be a preferential path.
Exactly.
Yeah.
But also, enable really the magma can move along those faults up if it happens, you know.
Yeah. I don't think so. Since if you look, I don't have here a section. No, maybe I don't have here a section. But if you look at sections, you can see that the inner part of the caldera is more or less up to 5 kilometers. Then the outer border are outside the range of the magma chamber. But of course, we know, who knows, it can be, of course. And then, very simply, just to explain you the mechanism that we hypothesize, this is a video, I don't want to show you all, but you can see here, this is the Pozzuoli arbor, so this one. See? This is more or less the sections that you see. This is the San Vito well, the one that we use it, and this is the inner caldera shape as we found. And you can see how you have this different formation. So this is the crater. Now you expect that this is the border. We have this degassing from the deep magmatic source, and we have this shallow layer of the caprock. The caprock is fibrous at a very micro scale, then can accommodate all this degassing, can deform before to have the rupture. And you can see here, just as a comparison, between the uplift that we have in Pozzuoli respect to one that we have in Yellowstone, the Long Valley Caldera. So it's very huge, the amounts of uplift that the caprock can accommodate. So, okay, here very briefly, but I don't want to go too deep into the data. So why it is important to characterize the seismic risk? This is something that is related to the ground shaking. So we can, once we know exactly where the events is and the magnitude related to this, we can construct this kind of curve that means the ground shaking at different places within the area that we are studying. So this is related to the seismic risk, of course. So characterize the seismicity is very important in order to construct a probability of occurrence of events in some areas. So we can say, okay, we have the probability in this point that the ground shaking exceeds this threshold. Then we need to be sure that our buildings, the peoples and so on are aware about this. Of course, as I said, the problem of Campi is a matrix problem. We have the seismicity, we have the volcanic problem, so you have also all the problem related to the pyroclastic fluxes. So you see, once the seismicity interests a very small part, but the volcanic eruption will interest practically all the Neapolitan, Neapolitan area. And here, very quickly, what is happening now? Since I report here the distribution of events. This is in red. This last month, and you can see how the uplifting the last phase becoming more reach a plateau. Also, the seismicity is lowering at least the numbers, but not the magnitude. We had another event, 3.5, very few days ago. So we cannot say what is happening. We can monitor the things. Thank you.
I'm afraid we don't have time for questions because the bus is about that we do, which is a shame because I had some questions, but I know where you are. So
Okay.
but
You can come.
the paper it show is still not published. Because I never saw this data. It's a huge amount of data.
Yeah.
Paper physically linked.
Yeah.
Finally, someone looked at the
Yeah.
word, not only the mathematics of the signal.
Yeah.
Wow.
We are trying to.
We are waiting.
We are waiting for the response. But I'm not so confident. You know?
Riuscita a fare qualche linea simile, adesso se avete qualche filo semplice, grande idea della profondità.
È complicato,
Sì.
Anche la scelta dei pittori, tutta la migrazione, questo fa male. Sì, ma non hai informazioni, cioè come lo fai comunque? Non hai, sai che io sono scrivere, l'incertezza che devo comprare è molto alta.